Okay, this is the version 2 of the Unit 4 practice exam. So I've got these two coils here. When the switch is closed, the pointer of the galvanometer is deflected towards the left. Now that the switch is closed, to make the galvanometer deflect to the right, one could do what? Well, let's assess what's going on here. We don't know the direction of the winding, so we don't know the direction of the magnetic field that's created by this loop. I'm going to just assume that it's in this direction. We're not worried about the right side yet. Just the left side is going to create a magnetic field towards the right. While B is increasing, there's going to be an induced magnetic field that goes to the left, because this is increasing the flux towards the right through loop Q, so it's going to create an induced current in the other direction to counteract that. So B induced is to the left, and B is to the right. I just assume the direction of this magnetic field to the right, so that means with that assumption, the induced field must go to the left. And that causes the galvanometer to go to the left. So in order to make the galvanometer go in the opposite direction, we need to do several things. We need to either decrease the flux. Well, yeah, we could decrease the current somehow in this circuit, which would decrease the magnetic field, which would cause decreasing flux. Or we could move this away, or we could do several different things. So let's go through our options. Well, the first says move the slide of the rheostat quickly to the right. So you've probably never seen a rheostat before. We didn't really talk about it, but it's a variable resistor, and if you move it to the right, that's going to decrease the resistance, so it's going to increase the current, which in turn increases the magnetic field, which makes the induced magnetic field increase to the left. That's no good because we want it to go in the opposite direction, which would mean the current was reversed. So that can't be an option. Move coil P towards coil Q, so that will increase the flux, and that will increase B induced to the left, just like before. We can't do that. We need to change the direction of the induced field. Move coil Q towards coil P. Well, that's the same thing. You're increasing the flux, you're moving them together. It's the same thing. Open the switch. That causes the current to decrease, which causes the magnetic field through this loop to go down, which causes the flux through this loop to also go down, which means that there's going to be an induced magnetic field in the same direction parallel to the magnetic field created by this loop, because as this magnetic field decreases, there's going to be an induced magnetic field that tries to reinforce the field, bring the flux through this loop back up to where it is. So that means that this is switched directions. The induced magnetic field now is going in this direction, which means the current through the circuit is going to switch directions. So the answer is D. Lines of magnetic field produced by a long straight wire carrying a current. This is a kind of a gimme question. According to the second right-hand rule, you point your thumb in the direction of the current and your fingers point in the direction of the magnetic field. So they do not, the magnetic field does not leave the wire radially. That's how electric fields would work. It's not in the direction of the current. No, that would also would be electric field. Oppose the direction of the current. No, just again electric field. Circles concentric with the wire. D. Lines similar to those produced by a bar magnet. No, not at all, because a bar magnet produces lines that go like this. Okay, so a long straight wire is in the plane of the rectangular conducting loop. The straight wire carries an increase in current in the direction shown. the current in the loop then is, okay, so using your second right-hand rule, point thumb in the direction of the current, so the magnetic field points in the direction of your fingers, which wraps around in that direction. So it's going to go like this. That means the magnetic field is into the page here and out of the page here. So in this loop, it's into the page and it's increasing, so that means be induced must oppose that by being directed out of the page. If the magnetic field induced is out of the page, so now I point my fingers, second right-hand rule, in the direction of the induced magnetic field, and my thumb points in the direction of the current, which is going to go counterclockwise around the loop. See, thumb in the direction of the current, fingers point in the direction of the field. The field is going to be up out of the page. I shouldn't have drawn it over here because over here the field is not into the page, it's just inside the loop. Okay, so in this next one, you've got two coils. This is really tricky, which is why I put this notice here. Note that the windings are reversed. You gotta keep that in mind. Okay, so hold on to that for a second. What I mean is when you start winding on this side, it passes in front of the core, whereas here it crosses behind the core. That's going to reverse any magnetic field caused by a current. Alright, so immediately after the switch here is closed, which one of the following statements is true? Well, if this switch is closed, this is going to create a magnetic field in this direction, which, keep in mind, the magnetic field extends back through this coil too. And as that's closed, this is increasing, so this must produce a induced magnetic field in the opposite direction. If this produces an induced magnetic field in the opposite direction, well, I'm looking at this wire passing in front of the coil, right hand rule, my thumb points in the direction of the current, which is down here, and my fingers curl. You can't really see this on the video. My fingers curl in the direction of the magnetic field, so that means current comes down and flows from right to left across this resistor. Again, the coil windings are reversed. You have to pay attention to that. So this is the opposite situation because the right side of the solenoid passes behind the coil. So you would expect that the current would be traveling left to right because it would be opposite of what the current's traveling here, but the windings are reversed, so it travels right to left. So assume the switch has been closed for a long time. Which of the following statements is true? Well, if the switch has been closed for a long time, this field is still here, but there's no change in flux. So in this case, flux through coil 2, we'll call it, does not equal 0, but dflux dt does equal 0. The change in flux equals 0 because the switch has been closed for a long time. So current will pass through this resistor because, why not? There's a power source here, there's a battery. But there will be no current through this because there's no change in flux. And so anything mentioning induced is gone. Magnetic field that points towards these are, you can go through them step by step. So the next one says that assume the switch has been closed for a long time. Which one of the following changes will result in an induced magnetic field in coil 2 that points towards C? So that is the original situation. It produces an induced current, an induced field that points towards C. So if the switch is opened, the first option, if the switch is opened, that's going to decrease, and there's going to decrease the field created here, and this coil will try to reinforce that field So it will induce a field in that direction, the opposite direction. So that cannot be an option. The iron core is removed from coil 1. Well, we didn't talk about this much. Removing the iron core will decrease the magnetic field, which is the same thing as opening the switch. It's just going to change the permeability of the space in the solenoid. Don't worry, I won't assign something on the test like that unless I warned you. All right, but let's look at the other option. Coil 1 and its core are moved towards A. Well, if you move this towards A, you're decreasing the flux through this, so that's going to want to create a field that increases the flux in that direction. Again, opposite direction. D, coil 1 and its core are moved towards B. Okay, so now we have the situation where all of this is moved towards this other coil, so that's going to increase the flux towards the left because we're moving it closer to the coil. So that's going to induce a field in the opposite direction to resist that change, to fight against that change. So that means the induced field would point towards C. That's our correct answer. It's two long parallel wires, each carry the same current in the same direction. What is the total magnetic field at point P between the wires? Well, we know the magnetic field due to a long straight wire is mu naught I over 2 pi r. These have the same current, and since it changes linearly, anywhere in the middle is going to have the same magnetic field, but especially right at the center, use your right hand rule number 2. The current points this way, so the magnetic field due to wire 1 must be into the plane, and the magnetic field due to wire 2 must be out. They're going to have the same magnitude because they're at the same distance, r, and they're in opposite directions. It must be 0. Incidentally, they're going to have the same magnitude anywhere in between the two because the r is to the power of 1. So if I add 1 centimeter of, move this point 1 centimeter closer to that one. Never mind, I take that back. Take it back. Take it back. All right. So is Ampere's law valid for all closed paths surrounding a conductor? Why is it not useful for calculating B at some point? Yes, it is valid everywhere. It's a matter of mathematics. So I've got some current with coming out of the page, and I'm going to draw a thick ring, although it doesn't have to be. This is my Amperian loop. There's some section of the loop, ds. I know because this is coming out of the page that B is in this direction. So if I were to draw the Amperian loop like this, still B dot ds around the closed path would equal mu naught I. It would always be valid. The problem would be at this situation here, I know because of the symmetry involved with the with this long straight wire, the magnetic field is in this direction, ds is in that direction. I'm going to have to factor that in when I say that this is the integral of B ds cosine theta. When I take that dot product, I introduce the cosine theta term, but that theta is going to be continuously changing because right here B is in this direction, ds is in that direction, cosine of theta is 1, theta is 0. That works. Here it gets more complicated, and then somewhere right here B is in that direction, ds is in this direction. The dot product between these two, theta is going to be 90 degrees, dot product is going to be 0. So in other words, I have to sum up all these different places, these different ds segments, and its product with B and the angle between it. The angle is constantly changing. We can't practically work with this Amperian loop. Even though this is mathematically valid, it's impractical to evaluate that. If I stick to a circular loop or something that matches the symmetry of the conductor, then B is always going to be in the direction of ds, and I can just say this simplifies to BS equals mu naught I, B equals mu naught I over S, and just because this is a circular loop with circular symmetry, I can say mu naught I over 2 pi r. That is the use. That is where, in other words, in order to use Ampere's law, you have to have a significant level of symmetry to make the calculation easier, just like with Gauss's law. So number 9, you got 4 wires of length L, 2L, or 3L. They move with the same speed. Rank them according to the maximum magnitude of the induced EMF least to greatest. Well, as they enter the magnetic field, the flux is going to be given by whatever L is, this side of the square, times whatever X is into the field at one time. So flux equals B A cosine theta. It's perpendicular. It's parallel, so no problem there. So this is equal to BLX. X changes as X equals Vt. Just from kinematics, they're all moving with the same velocity, so at a certain time point, X is going to be the same. So phi B equals BLVT. Now, V is the same for every one of these shapes. T is the same because they're all varying at the same time. B is the same. The only difference is L, because remember, L is always this side. So the greater this L, the greater the EMF induced due to Faraday's law. T equals negative N, and I don't have to put the N in there because each loop only has one turn. D dt BLVT equals negative BLV. So the induced EMF is proportional to L. 4 has the largest L. 3 is next, and that equals 2, and 2 is greater than 1. One, two, three, 4. So this side right here doesn't really matter, because yes, eventually it's going to gain more flux than the other two. You could even say it's going to induce an EMF for a longer period of time, but the magnitude of the EMF depends just on how quickly the flux is changing, and the larger this side of the loop, the faster the flux is changing. So if you have a long solenoid and current is running through that solenoid, on each, so let's say I just look at the windings, the windings that are on my side, and then the solenoid, the other windings are on the other side, the near side. Then in that case, if the current comes in, like current's coming in here, and it's going like this, on my side, the current will always be flowing up. And then on the other side, it's going to flow down, but on my side, it always flows up. So that means, according to each wire, the wire to the right and the wire to the left is going to be traveling with current in the same direction. So that is attractive. So they're going to attract each other, and they're going to squeeze the solenoid. Why is that? Well, if you have current I, right-hand rule number 2, that's going to create a magnetic field in this direction, or into the plane over here, out of the plane over here. If I have another I over here, we'll call this 1, 2, then from the Lorentzian force, I2L cross B1. So this one sets up a magnetic field out of the plane. If I do the cross product, I2 out of the plane, curl my fingers in the direction of the magnetic field, my thumb points in the direction of the force, so the force is in that direction. You repeat the process on the other side, force in that direction. So it's an attractive force. This problem's kind of tough. This wants you to know the magnetic field of the third vertex at P is. Well, this one requires you to, and they both carrying the same current out of the page. This one requires you to do a bunch of trigonometry. So if I draw the circle over here, current out of the page, current out of the page, use right-hand rule, thumb in the direction of current, magnetic field, circles in the direction of your fingers. They're each going to create counterclockwise currents. So that means at point P, the magnetic field from 1, call this 2, is going to be curved like that, and the magnetic field from 2 is going to be curved like that. Or if we just, those are the field lines, if we draw the vectors, then we can draw the vectors. When I draw the vectors, we can draw them as B2 and B1. And remember that these magnetic fields form a right angle with the straight line distance to the wires themselves. So in other words, B2, B1, because this is a right angle and that is a right angle. That's a property of circles, right? You draw a straight line point on the circle, magnetic field points tangent to that circle, which means it's a right angle. All right, so we have to think about angles for a little bit. So let's say I have two parallel lines and put an equilateral triangle between them. These angles are all 60 degrees, right? That's 60 degrees. These sum to 180, and these two have to be equal, so that means this is 60 degrees as well. That's one property. Another thing you can think about is, so this is the line to wire 2. This is 60 degrees, as we just showed above. The triangle itself makes a 60-degree angle, and then this magnetic field, which we said is at right angles. Remember, a right angle is 90 degrees. That's 60 plus something equals 90, so this must be 30 degrees. 60 plus 60 is 120, plus 30 is 150, so this must be 30 degrees as well. And when you draw the other magnetic field, then it's going to be 30 there too. I didn't draw the angles very accurately, but the reasoning is sound. So if I want to go back and draw like a free body type diagram, I've got B2 at an angle of 30 degrees, and I have B1 at an angle of 30 degrees. And so now I just have to add these two things together. So B1, the vector B1 is equal to negative, actually first let me come over here and define something. So the magnitude of B1, we know it's going to be the same as the magnitude of B2 because they have the same current. That equals mu naught I over 2 pi r, where r is 4 centimeters. So I'm just going to define this generic B as mu naught I over 2 pi 4 centimeters. You can call it however you want to do that. Okay, so the vector B1 is equal to the magnitude of B1 times cosine of 30 degrees, and that's going to be in the x direction, or I hat direction, plus, because it's positive in the y direction, the magnitude of B1 times sine of 30 degrees, j hat. Well, I can sub in my newly defined B for B1, so this is b, and actually I'm going to factor b out because it's in both terms. So negative cosine of 30, well, if you remember your unit circle, got pi over 2 up here, pi over 4 down there, pi over 3, and this is pi over 6, and that equals 30 degrees. Well, the coordinates of pi over 6, cosine of pi over 6 equals square root of 3 over 2, and sine of pi over 6, remember sine is the smaller one because it's the vertical distance, that equals 1/2. 1/2. So now I can put that in here for negative cosine of 30 is square root of 3 over 2 I hat plus sine of 30, which is 1/2 a hat. If I wanted to, I could factor out the 2, so it's 1/2 b times minus square root of 3 I hat plus j hat. So let's look at B2. B2 is going to be same thing. It's going to be b, actually it's going to be negative b cosine of 30 degrees I hat minus b sine of 30 degrees j hat. So it's going to equal negative b times cosine of 30 square root of 3 over 2 hat plus, because both the negative sign has been factored out, 1/2 j hat. Or you can write it as negative b over 2 times square root through 3 I hat plus 1/2 j hat. So then the sum of both then is just, we're going to add b1 plus b2, which we have to add the I hat components and the j hat components, the x components and the y components. So I'm going to circle these. So they both have b over 2. So I can pull that out. The b1 is negative square root of 3 minus square root of 3 I hat. I distributed that negative sign. So that's going to equal 0. Plus, well, that would just be 1 minus, oh, I made a mistake. Factored out that too. So that'd be 1 Oh, I'm sorry. I said this would equal 0. It's not going to equal 0 because they're adding together. My fault. So that's b over 2 times negative 2 square root of 3 I hat plus 0 j hat. 1 minus 1 is 0. That makes sense because y components cancel, x components double. So it's negative b, the 2's cancel out, square root of 3 I hat, which is negative square root of 3 mu naught I over 2 pi r, where r is 4 centimeters. And if you plug in the numbers, that equals negative 17.3 microtesla in the I hat direction. But the problem just asks for the magnitude. So this is 17.3 microtesla. Okay, so in this one you're given magnetic field equals 3.0 Tesla, phi equals 90 degrees, r, the radius of the circle, is 0.024 meters. We're also told that the loop is pulled out of the region that contains the field in 0.2 seconds. What is the rate of energy dissipated in r? Well, we know that the area initially is pi r squared, and final is 0 because the loop is completely pulled out of the magnetic field. So we also know there's only one winding. Okay, so if we go to Faraday's law, what are we looking for? We're the rate of energy dissipated in r. Power equals I squared r, which equals IV. Well, we don't know what V is, we don't know what I is, we do know what R is, so what I'm going to do is I'm going to plug in I equals V over R. I'll plug that in for I times R, so that's V squared over R. Power equals V squared over R. If I find the induced EMF, the induced voltage, I've got the resistance I can calculate. So going to Faraday's law, d phi over dt. So Faraday's law, the induced voltage is equal to negative the number of turns, in this case it's just one, times the time rate of change of flux, which I can simplify down to BA cosine of phi here. Phi equals 0 because the magnetic field is in the same direction as the area vector of this loop. So that makes it a little simple. We also know that the magnetic field is not changing. So this is negative B dA dt. Now, one thing that the problem didn't say is it didn't say the average rate of energy dissipated in R. I will go back and add that to the problem because you have to put that average in there, because when you do, I'm going to put the bar for average, I can then say negative B delta A over delta T. So this equals negative B A final minus A initial over T final minus T initial. Initial time is at 0, final area is 0, so this just equals to B AI over TF. And this equals then the magnetic field. Well, I'll leave it as that right there for now. So go back to our power equation. Power equals V squared over R. So this equals 1 over R times B A initial over T final squared, where area is pi r squared so we can plug all these numbers in. And the power comes out to 0.491 milliwatts. Alright, so the conducting loop has an area 0.065 meters squared. Phi is 90 degrees. Phi is 0 degrees because the loop is perpendicular to the magnetic field, but the area vector is in the same direction. So loop, area vector, and the magnetic field is in the same direction. So magnetic field decreases, so I'm going to say the final magnetic field is 0.30 Tesla. And the amount of time that takes to happen is 0.087 seconds. And we are also told that the average induced EMF is 1.2 volts. So we need to find the initial magnetic field. Magnetic field, yes. Oh, we also know that it's only one loop, so n equals 1. So we go to Faraday's law, but we don't have to use this because we know that we can approximate this using the average induced EMF equals -1. I'm going to say that's, just drop that in immediately because it's 1. So that's negative delta, because we're talking about average, magnetic flux, which is BA cosine phi over delta t. Well, we know cosine of phi is 1. And we know that the area remains constant the whole time, so it's negative area times delta B over delta t. So the average EMF is negative A, B final minus B initial over T final minus T initial. We can say T initial is 0. We can also say, okay, so we know what the final is. We need to solve for the initial. Okay, so now it's just a matter of algebra. And I can multiply TF there equals BF minus B initial. Move the B initial over here, move this stuff over there. So B initial equals B final plus the average EMF over area times T final. And now it's just a matter of plugging in numbers. So B initial is 1.91 Tesla. This one's a little more interesting. We have an LR circuit, got a battery, L, there's a resistor, L equals 8.0 millihenry, and resistance equals 2.0 ohms. So we want to know at which time the current reaches half its final value at a time of what? Find time when I equals 1/2 I max. So we go to our equation for the current passing through an inductor in an RL circuit. Okay, we also note that this is the maximum current that will flow through. From Ohm's law, V equals IR or epsilon equals IR, however you want to write it. So I can rewrite this equation as I equals I max 1 minus e to the negative RT over L. And I want to find T when I is 1/2 I max. Well, you know, I max cancels out of each side, so 1/2 equals 1 minus e to the negative RT over L. I've got to isolate this logarithmic exponential, so e is negative RT over L equals 1 minus 1/2, which is going to be 1/2. So I'm going to raise each side, take the natural logarithm of each side, which undoes this logarithmic exponential. So this becomes negative RT over L equals natural log of 1/2. took the natural log of both sides. This 1 minus 1/2 is 1/2. So now it's just solving for t. Negative L over R, natural log of 1/2. Does this make sense? Well, natural log of anything between 0 and 1 is going to be negative. So negative times negative, positive, and plug in the numbers. T equals 2.77 milliseconds. And that's everything.